There's yttrium, terbium, actinium, rubidium, boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium.
Before I go deeper into this dot point, I quickly want to talk about the role of the ozone layer again. The ozone layer was a protective layer, and it was in the stratosphere. So this roughly here would be the stratosphere, which is the upper atmosphere. So the upper atmosphere, that's where the ozone layer can be found. And what it does, it prevents the UVB rays, not all UV rays, but UVB rays specifically, from hitting the Earth's surface. And we're going to cover in a couple of minutes what the UVB rays actually do, but they, for example, cause skin cancer, etc. So ozone layers are quite important because they can block the UVB rays right here, and that means that we have less problems on the surface of the Earth, such as skin cancer, etc., etc. So that's what the ozone layer does, and it's quite useful. But what we're going to do in this video is we're going to discuss the problems associated with the use of CFCs. So we're going to discuss problems, what do CFCs do, and also we're going to assess the effectiveness of steps taken to alleviate these problems. Right, so first, what are the problems? And second, what have we done to try to solve the problem? Alright, so first of all, what is the problem? Well, the problem itself is that these CFCs, and the best example would be trichlorofluoromethane, right? That is this one here. Or, so the common name is CFC11, that's the most commonly used CFC. And its structure formula would be as following. It would be carbon in the middle. That has a methane name, which is one carbon. And then it has 3 chlorines attached. And it has one fluorine attached as well. Right, this is CFC11. Now, you actually need to know these two. There's going to be 3 equations you should definitely know. First 2 are here, and the next one will be in the next page. This one here is what happens when CFC11 gets in the stratosphere. So this happens in the stratosphere, right? Not in the troposphere, not in the lower atmosphere, but in the upper atmosphere of the stratosphere. So we've got CFC11, which is this here, and it comes in contact with the UV radiation. So this is not UV, just any UV radiation, but usually UVB radiation. So one CFC comes in contact with UVB radiation, which would be in the upper atmosphere, the stratosphere. What will happen is you're going to have one of these chlorines, right? So one of these chlorines here, this bond here, this is where light, so the photons of the UV ray hit and break this bond. This bond gets broken. And what you can see is it has, now it's called, so after it's being hit by UV radiation, it's called CFCCl2, and that's a radical, and there's a Cl radical as well. So we have 2 radicals being formed. Now these radicals will cause problems, especially the chlorine radical. This is the one which is for us most problematic, or for ozone most problematic, and that can be shown in step 2, right? So step 1 is all about how we create the chlorine radical. That's when UV radiation or UVB radiation hits the CFC molecule in the upper stratosphere, or upper atmosphere, being the stratosphere. And then we have this chlorine molecule attacking, because it's a radical, right? Radicals are very aggressive. It will attack ozone. So ozone being O3, and this is all gaseous, obviously. And then what happens is we have this molecule being formed, but more importantly, you can see ozone being gone, right? So we have a radical being formed and oxygen being formed. But the problem is ozone has decomposed. It's gone back into oxygen. It's not ozone anymore. So this is an example of how we can start with a CFC molecule and end up having no more ozone left. It's broken down ozone. And what we're going to show you in a second is the problem that comes when it comes to this being a chain reaction, right? This is not just happening once, but it happens over and over again. So this one CFC molecule can basically destroy thousands, if not tens of thousands of ozone molecules. I'm going to go over that in a second. But you should know something called the ozone depletion potential, or also sort of shortcut for it would be ODP, standing for ozone depletion potential. Now CFC11, this is kind of considered our standard. This is what we compare all the other ones to. This is also one of the most commonly used ones, or used to be one of the most commonly used ones. We've kind of phased it out now. But it has a ODP, ozone depletion potential, of 1.0. So 1.01 is CFC, and then we compare all the other things to it. So for example, some other CFCs, such as CFC 113 or or CFC 115 have 0.8 or 0.6 ODP. So I still have some ozone depletion potential, but a bit less than the original one. Right? So I'm going to go back to the original slide. I'm going to add some more to it. So we talked about the ozone layer being in the stratosphere. We talked about its function. It's trying to prevent UVB radiation hitting the atmosphere, so the Earth's surface. And these two reactions are these two chemical equations I showed you just now. Number one was how CFC11 reacts with ozone with UV radiation here in the ozone to form this chlorine radical. And then this chlorine radical in the second equation will attack ozone and form normal oxygen again. And it will also form this one here, which is just a radical, not a radical. Now, all this happens in the ozone layer. And the problem is because this has formed, what you're going to see in a second, in the third equation you should also know, is this is the chain reaction part of the whole problem. So chain reaction, what I mean by that is that one single CFC molecule doesn't just destroy one ozone molecule. It can destroy, let's say, thousands, if not tens of thousands of ozone molecules. Just one single one, which means we only need to have a tiny amount up there for it to cause major problems. And the reason why it can cause any problems is because this product, which was formed from the second equation, can be reformed into a chlorine radical, right? So this won't cause any major problems for ozone. But because we also have, just like we have in the ozone layer, we have some random oxygen radicals floating around. We'll always have it, especially because there's lots of UV radiation which will make them happen, right? So we're going to have these ones there as well. So once this forms, which forms in the second step, the chlorine, which is also going to be here now, so the chlorine oxygen radical will be here. When these two meet, when they combine, what will happen is we're going to have normal oxygen being formed, but we're going to have our problematic chlorine radical forming again, right? So this original one, which was the one that actually attacks ozone, will reform when a chlorine oxygen radical meets an oxygen radical, and that happens in the stratosphere after reaction 2, right? And that means once we have this, then this can start again, chlorine breaking down ozone. And this will happen over and over again, so it's going to be a cycle, a continuous cycle. And that's why one single CFC molecule can result in the destruction of tens of thousands of ozone molecules. Now, what happens if our ozone is gone? As I mentioned, ozone is meant to protect UV from not reaching the Earth's surface. More specifically, UVB radiation. It absorbs the vast majority of UVB radiation. Now, if we have less of it, obviously that means we're going to have more of it coming to the surface of the Earth, right? So more will hit the actual surface. What does it cause in terms of problems for us or for our environment? Well, some of the problems are that it causes severe sunburn and skin cancer, right? So it's not just sunburn, but severe sunburn and skin cancer. It causes eye cataracts. That's when you go blind. You know, when you see that whiteness in people's eyes, that often means they have too much sun damage and their eyes can't see anymore. It destroys parts of their vision. And also even reduce plant growth. So for example, if we have an ozone hole, or more UV radiation comes through, well, especially UVB radiation, that means the actual crop yield, so how much, for example, how much wheat we can grow or how much corn we can grow, will also be reduced because that UVB radiation damages crop growth, right? So it reduces plant growth. And also it can even damage polymers, especially your chloro, so PVC, and we mentioned PVC a while ago in the production of materials module. The PVC has chlorine, carbon bonds, and this UVB radiation will break those bonds in that polymer, which means it will break PVC polymers. So these are some of the problems when we have more UVB radiation, and the reason why we would have more UVB radiation would be because of more CFC being in our atmosphere due to the problem mentioned here. And I'm going to go over all those equations in the next video as well, so if you're still a bit confused, don't worry about it. But I still have to talk about the second part, which is assess the effectiveness of steps taken to alleviate these problems. So what have we done to try to reverse this problem? Well, first of all, we realized it was actually a problem. We didn't know that for a long time. But by the 1970s and the 1980s, we kind of discovered, oh, we actually have a problem. We need to monitor our ozone because it seems to be going less and less. And we were quite effective at doing that. So we know a lot more about ozone now. So we know a lot more about ozone. And we know a lot more about what destroys ozone than we did beforehand. And the reason why is because we put a lot of money into researching ozone and ozone destruction ever since we found out that ozone is actually being depleted. So that's one of the problems, but one of the steps we've taken to solve the problem. We've tried to research more about ozone, and we've found out quite a bit about it. The second step, and so that was quite effective. Monitoring, we've been quite effective at it. The phasing out part. So the phasing out was introduced by the Montreal, and you should know this one, the Montreal Protocol, which is when basically many of the world leaders came together in 1987 to think of a way that we can try to get rid of CFC to stop ozone depletion. And this was actually one of the most successful protocols sort of ever. We've tried to do it with global warming. We've not been very effective. But the Montreal Protocol has been relatively effective, right? So we've been, for example, all the developed countries, so Australia, America, Europe, Europe is not a country, but countries in Europe, they have more or less phased out CFCs, generally by kind of 1986. So that was, 1996, that was when they wanted to phase out CFCs. The developing countries have had a bit longer time to get rid of their CFCs. But overall, we've been trying to get rid of CFCs as much as possible, and we've been quite effective at doing it. The developing countries still have a bit of a leeway, so they still have a bit more time to phase out some of the problems when it comes to CFCs and some of the alternatives, the replacements such as hydrofluorocarbons. I'll talk more about those next couple of years as well. But overall, phasing has been quite effective, but we still actually have ozone damage occurring, even though we're phasing it out, and I'm going to talk about that also in a couple of years' time. Replacements, we have worked on two different types of replacements. We have dealt with HFCs, and we've dealt with CFCs. These two are replacements which are meant to be having a smaller ODP, ozone depletion potential, and they have been quite effective. This is still damaging the ozone, but it was kind of seen as a short-term solution to the problem, whereas CFCs was considered to be a long-term solution to problems. The other way around. This is the short-term solution, and this is the long-term solution. But the idea is just to have an alternative which is less damaging to the environment. And again, it's going to be a whole document on those, so I won't have to go into too much detail on this. But just in terms of evaluate the success, overall we've had good success with the Montreal Protocol, phasing out, finding replacements, but we actually still have an ozone hole. And that's one of the reasons why, is because what I'm going to cover now, it's the last part of this video, and that was that these are actually, so the CFCs are inert. CFCs are inert, that means they don't react. They are non-soluble in water. And they also have a very long lifespan, so a very long lifespan. So they don't decompose easily, especially once they get in the stratosphere. So what that means, inert means that, for example, many chemicals, once in a troposphere, they might react with something else, right? So many chemicals, if they are not inert, if they are actually reactive, that means they're going to react with something else and they're going to be gone because they have reactive with something, right? So they're going to be gone. But the problem with CFCs is they're non-reactive, which means they can get all the way in the stratosphere. There's nothing that will block them. There's nothing that will react with them until they get in the stratosphere. And obviously, once they are in the stratosphere, then you're going to have UVB radiation breaking them apart to a degree. But that's obviously, the breaking apart in that case was actually bad. But because they're non-reactive and inert, that means they can actually get in the stratosphere. Also, they are non-soluble, which means that they, for example, if there were rain, right? So usually there's rain, and rain will wash things down that are soluble. So if it's soluble, it would have just been washed back down to Earth, and it wouldn't have reached the stratosphere. But because it's non-soluble, CFCs are non-soluble, that means they won't be affected by rain. It can rain as much as it wants, it doesn't matter. It's eventually going to creep into the ozone layer. That's another problem. And the third problem is it has a very long lifespan, which means it can actually survive there for hundreds of years, basically, right? So this chlorine form, these chain reactions can go ahead for hundreds of years before it stops. And that's also a massive problem, because now these three problems have meant that any CFCs we've used, even if we only use a small amount, that means they're going to get into our stratosphere eventually, and they're going to stay there for a long time. So even though we've basically stopped using CFCs completely, we still have a problem, because they're going to stay there for a while. Even the ones we've used 20 years ago are going to cause problems for some time to come, right? So when it says assess the effectiveness of steps taken to alleviate these problems, we have been quite effective at phasing it out, at monitoring the whole problems, at finding replacements. But even so, we still have a problem because anything that we've used 20 years ago, or 30 years ago, 10 years ago, would have still been in the atmosphere and stratosphere, and it's still causing problems. So we're going to have to wait some time for it to be completely gone, simply because of the whole fact that even a small amount that we did use, all have gotten in the stratosphere, and they're going to stay there for quite some time. Right? So that's what you should also know. But hopefully that was useful.
Thank you for watching.